Let's get some old exam practice. We need to determine the magnitudes of the tensions T1 and T2 in this diagram. So notice here we have an 80 kilogram stone hanging from a string over there, and then the string splits into two, and this string here is being pulled with a tension T1, and this string here going over this pulley is being pulled with a tension T2, and we can see the angles here between the three strings. So the first thing we realize is, of course, gravity is going to be pulling this stone downward. We're going to make all the forces act on this point. Whenever you draw a free body diagram, you have to take one point and draw the forces acting on that one point. So of course it's true that the weight of the stone actually acts from the center of the stone, but here I'm drawing it as if it comes from the center of the three strings. But of course the weight also pulls down from the center, so it is correct what I've drawn here. So we have the weight acting downward. Next, we realize that tension 1 is acting from this join in the strings upwards and to the right. Of course, we have T1 written there, but notice that its direction has just been altered by the pulley, but for the area here, its direction is as shown there. So instead of being confused by the fact that the pulley has altered the direction, just ignore the pulley's effect and remember we are just focusing on the forces acting on this point. Also, this 120 degrees is not so useful. More useful would be this angle here. How much is that angle? Well, here I've drawn a horizontal line, so this here must be 90 degrees because weight always acts vertically down. So this is the y plane, the vertical plane. So this angle here has to be 90 degrees. And this 120 degrees includes the 90 plus some more, and it's the some more that we're really interested in. So that some more must be 120 degrees minus that 90 down there, which is equal to 30 degrees. What else is acting on this point? Tension 2. Again, yes, the pulley has changed the direction there, but don't let that confuse you. At this point here that we're interested in, tension 2 is acting in the direction shown there. Again, this 140 is not of so much use to us, but we can again draw in this construction line here, which is at 90 degrees to the vertical, and then we know that this whole 140 minus the 90 gives us this angle that we're really more interested in, which must be 50 degrees. So this diagram here, which is a free body diagram laid on top of the picture, is of more use to us. So let's work with it. So I'm just going to fade out and later even take away the picture. Right, now we know that we should take G as 10 meters per second squared. And weight is equal to mass multiplied by acceleration due to gravity, G. The mass is 80 kilograms and G we're told to take as 10. 80 times 10 is 800 and the unit of weight is newtons. So we know the magnitude and of course the direction of the weight. It's 800 newtons downwards. Now it's important for us to realize that this situation we have here is in equilibrium. What does that mean? What does equilibrium mean? It means that there's no acceleration. The stone is not falling, nor is it rising. It's not accelerating in any direction. Actually, it's even stationary. It doesn't even have any motion at all, never mind acceleration. But whenever there's no motion, there's also no acceleration. So certainly it is in equilibrium. Whenever forces are in equilibrium, the resultant is zero. How can we tell that the resultant is zero? If we rearrange the free body diagram so that we have tail, head, tail, head, tail, head. So we rearrange the free body diagram so that the vectors follow one another. Then we will get a closed diagram. In other words, no resultant. So that must be the case here because we know that this is in equilibrium because there isn't any acceleration of that stone. Everything is stationary and therefore there can be no acceleration. So we use this fact to solve the problem. And we can do that with either of two methods. The first one is using an accurate scale construction, which means that we have to draw these forces to scale and with the right angles. And we have to move them to make a closed vector diagram, and they must close. That vector diagram must close because it's in equilibrium. So we could move the T2 vector up so that its tail is on the head of the T1 vector. And we move the weight up. And you see we have a closed vector diagram where we have tail, head, tail, head, tail, head, everything following in the same direction, no resultant. So this then would be the diagram that we would have. However, the angles as shown there might not be so very helpful to us. So let's think a little about what other angles we can deduce. These two construction lines are both to the horizontal, so they are parallel to one another. So here we have alternate angles. It makes a Z, and these are alternate angles. Alternate angles are always equal. So we knew that this one was 30. Go back and see how we knew that if you can't remember. And therefore this one must also be 30 due to alternate angles being equal. We know that this is a right angle triangle. How do we know? Because the weight must always be vertically down, and this construction line was to the horizontal. So they have to be at right angles to one another. So this has to be 60 because the whole here is 90. Take away this 30, and that leaves us with 60 there. So there's another angle we know. Then we see that these two together equal 80. 50 plus 30, 80 degrees. And we know the angles of a triangle always add up to 180 degrees. So what must this angle here be? So that 60 plus 80 plus this angle makes 180 degrees. I hope you can see that it must be 40. 40 plus 60 makes 100. Plus 80 makes 180. So using this information here, we can then find out by scale diagram the magnitude of T2 and T1, which is what we were asked. Now this is not the only way to do a scale diagram, because notice to get here I had to move T2 and W. But I don't have to move T2. I could rather move T1. So let's go back. We go back to our original diagram, our in situ diagram, our free body diagram. And now I'm rather going to move T1. So I move T1 so that its tail is on the head of T2. Then of course I must also move W so that its tail is on the head of T1. And we have a closed vector diagram because this is in equilibrium. Again, these particular angles shown are not that useful. So let's think about what else we know. This here must be 90 degrees because weight always acts vertically down, and this is a horizontal construction line. And so therefore that there must be 40 degrees, so that 40 plus 50 equals 90. These two construction lines are both horizontal, and so they are parallel to one another. So here we have alternate angles. Alternate angles are always equal. We already knew that this one was 50, so that must also be 50. These two together make 80 degrees. 30 plus 50 is 80. So what must this one be? Because the angles of a triangle must equal 180. I hope you can see that it must be 60. 60 plus 40 gives 100 plus 80 gives 180. So here I've just replicated the two diagrams that I gave previously. They are both right, and they will both give you the right answer. Go back to see how they correspond. So you can draw a scale diagram. Maybe you will say your scale is 1 centimeter represents 100 newtons. So then the one value that is known is the weight, 800 newtons. So you would draw that 8 centimeters. Note, you don't need to do both of these diagrams. You do one or the other. Then you know the angles. Look back to see how you know the angles. This one must be 60, that must be 40. Let's say we're doing the first diagram. So you must draw this weight vertically, 8 centimeters exactly, with a sharp pencil. Then you must use a protractor and measure 60 degrees here, and then draw a line. You won't know how long to draw it, you just draw it. You just extend. With a ruler, not skew like I've got it there, of course. And then over here, you'll measure 40 degrees very accurately with your protractor, make a dot, and then draw this line, and you won't know how long, well, you will actually, because where the two meet, that's where your lines must stop. And once you've drawn that, then you measure how long is this, and you'll find that it will be 5,2 centimeters. You convert it according to your scale, that's 520 newtons. And when you measure this line, if you use this scale, you'll measure it to be 7 centimeters, convert it according to your scale, 700 newtons. And then you have your answers. T2, 700 newtons, T1, 520 newtons. Same procedure if you rather choose this one. Both diagrams are equivalent.